For this second example, we have basically the same concept, but instead of hanging in the air, M1 is now lying on a surface. And the surface has friction, so it's going to stop a little bit more the second mass. But still, the second mass is heavy enough to go down and pull M1 with it. So now M1 is going to move to the right, and M2 is going to fall downwards. So to solve this problem, we use basically the same exact steps as the previous problem, but now we take into account that the coefficient of friction between mass 1 and the table is 0.07. We have masses, again, different masses, so mass 1 is now 6 kilograms and mass 2 is 1 kilogram. And we want to find the acceleration of the two masses and the tension in the string. Remember, there's only one acceleration and one tension. So we want to find that. So again, our first step, as always, is to draw a free body diagram for each mass. So we have mass 1, and mass 2. Okay, so we do exactly the same thing. We start with the force that is always there, no matter where the mass is or what it's doing, and that's the force of gravity. So we have here force of gravity for this one, and force of gravity for this one. Now, this one, M2, has a tension going upwards, right? Because it's trying to go down and the string is pulling it up. So we have tension upwards. Probably should have done it in pink like in the other example, but who cares? Those are the only two forces acting on M2 because it's not on a surface, it's not feeling air resistance, nothing else. So we're done with this free body diagram. But this one is still missing a couple of things. So tension, again, there's a string, but this time tension is not upwards because the string isn't pulling up. The string is going to pull the mass to the right when the system moves to the right. So tension in this case is to the right. Yeah? But we're missing more forces. Now the object is on a table. So if it is on a table, there has to be a normal force. We can't forget normal force. If there was no normal force, this object would be falling downwards, and it's not going to fall downwards because of the table. So we have a normal force. It's perpendicular to the table, so it goes upwards because the table is horizontal. And we're missing one last force because there's friction between the box and the table, and it's stopping it. If the box is trying to move to the right, friction is going to move to the left. So we have a friction here, a friction force to the left. So as you can see, this example is a little bit more complicated than the previous example, but it's just following the same simple steps and you'll be done. You don't have to worry about it. So we can start by finding the weight of each of these blocks, so that we at least have that. So the weight here, this one has a mass of 6, so weight, which is m times g, is 6 times 9.8, which I'm going to have to get my calculator to get, but it's about 55 or something. 6 times 9.8. Nope, 58.8. Let's put it here. 58.8 newtons. And this one is easier to do. Mass times gravity, but the mass is 1, so it's 1 times 9.8, which is just 9.8 newtons. Okay, so now that we have that, we can continue with Newton's second law for each. So remember, writing the Newton's second law, we do it separately, and then when we have our two equations with two unknowns is when we mix them together. But for now, it's just doing this as two separate problems. So let's try with this one, which is easier, mass 2. So we have two forces, and again, we're going to take as positive the direction of motion. So this one will be moving downwards, so we take weight as positive. So we put, okay, so we have to do our equation. Net force is mass times acceleration, and our net force is a positive weight of 9.8 minus a negative tension. Those are the only two forces. We only have two arrows in our diagram, so we can equal that to mass times acceleration. This is m2, which has a mass of 1, times a. 1 times a is just a. So what I would do is just get rid of this 1. So you have 9.8 minus t equals a. But if you prefer to have it there just to know that 1 is the mass, that's perfectly fine. Okay, and that's it. That's our equation for mass 2, and we already have our tension and our acceleration, so we wait for this one to be ready in order to mix them, but we leave this one on the side. So now let's go with this one, which is, as I said, a little bit harder. So now the direction of motion is to the right. So we can start with our equation that is up and down. Remember that I told you last class that we start with the easy direction. So this one has 2 dimensions, vertical and horizontal. So we need to do our 2 equations of motion. So we're going to do vertical first, because it's the one that has no motion, so it's easier, and horizontal later. So for vertical, we have 2 forces, normal force and gravity. So we have, there's not going to be an acceleration, so it doesn't matter which one we take positive and which one we take negative. But we usually say that up is positive, so let's just put Fn as positive. And we subtract the weight, which was 58.8. Now that is equal to mass times acceleration. But remember, there is no acceleration vertically, so the acceleration is 0. So we're going to have here a 0. So this is actually a very simple equation to solve. We just need to pass this to add to the other side and solve for normal force. So we get normal force equals 0 plus 58.8 is just 58.8. So this makes sense because in this case, that the box is not inclined or slanted, normal force should be equal to the weight because there's no acceleration in this direction, so they have to cancel themselves out. So it does make sense that in this case, normal force is exactly the same as the weight. But it's still good practice to do it separately, just so that we don't get confused with inclined planes from last class. So we did what we could with vertical. Now we move on to horizontal, which has what we actually care about. So again, we're going to do net force is mass times acceleration. So now for horizontal, we have the direction of motion is right, so we take tension as positive, so we have tension minus, and the opposing force is friction. And this is going to be equal to mass, which in mass 1 is 6, times A. So before we can unite it with this one and solve the system, we're going to have to find friction force. So let's get on with that first. So remember that friction force is mu times normal force. Mu was given in the problem, it's 0.07. And normal force, we just found it, it's 58.8. So we can calculate this with our calculators. So 0.07 times 58.8 gives us 4.116 newtons. This is friction. Okay, so now we can go back and finish off our equation for horizontal by putting friction into FF. So we had tension minus, and now we know friction is 4.116. That's this, equals 6 times A. So that's it. Again, we have our 2 equations with 2 unknowns, T and A. So we can do what we did the last time, which is pass this equation right below here and add them. So that's what I'm going to do. I'm going to get this one plus T minus 4.116 equals 6A. Okay, so let me just erase this for space. And we can put this little line and add our 2 equations together. So again, we're going to add the left side with the left side, the right side with the right side. And exactly the same thing is going to happen as in the previous example. We have a 9.8, and a negative 4.116, which we're going to get here. And then we have a positive t and a negative t, which are going to cancel themselves out. So t minus t cancels each other out. So we are only left with the 9.8 plus negative 4.116 equals, and now we add the other side. So we have 1a plus 6a gives us a total of 7a, just 1 plus 6. Okay, so now that we have a single equation, we solve this side. So we have 9.8 minus 4.116 gives us 5.684 equals 7a. Okay, so finally, we take this up here. So we had 5.684 equals 7a. So to solve for a, we divide by 7, right? This 7 is multiplying by a. We divide on the other side, so we get 5.684 over 7, and that's a. So again, we put that in our calculators because we don't know how to do that in our heads, and we get 0.812 meters per second squared. That's our acceleration. Good. So again, we solved it by adding these two equations and canceling tension out. And the final step, again, is to use this acceleration in either of these equations to solve for the tension. So we get that A, and let's put it in here, which has tension positive, so this one down here. So we have tension minus, I'm just copying this one, minus 4.116 equals 6 times A, and A was 0.812. So T minus 4.116 equals, I'm going to put this in the calculator, so that's 6 times 0.812, which is 4.872. And final step is T is here, subtracted is this, so we have to add it on the other side. So we get that T is what we had, 4.872 plus 4.116. Put it in the calculator. So add 4.872 plus 4.116, and we get finally 8.988. So just want to keep our color scheme. So finally, T is equal to 8.988 newtons. And that's it. Our two equations are two unknowns. Again, as I told you before, if when you already have these two equations, you want to put them in your calculator and let the calculator solve them, if you know how to do that, that's perfectly fine. You don't have to do this math if you know how to do it a different way. Or you can solve for T in this equation and plug it in here, which is called substitution, elimination, any method that you want. This is just my method. But as long as you get to these two equations, that's the physics part, that's what I care about, and then you solve however you want the math part, which is just practicing your algebra. But this is how you solve every single type of pulley problem. So you first draw the free body diagrams, then you get a Newton's second law equation for each of your masses, and then you solve the system of equations to find acceleration and tension using both equations at the same time. That's it.